Hi, this video is all about supremums and infimums. First, I will give you the definition and explain what a supremum is, and then we're going to solve a lot of problems, 13, in increasing difficulty order. So I will give you the timestamp, so if you just want to solve problems with me, you can start from there. So I will start with the definition. If we have a set that has an upper bound, then it has infinitely many upper bounds. So the supremum has to satisfy two conditions in total. And if it does satisfy both, then it is a supremum. The first condition is that it must be one of the upper bounds. As I said, one of the infinitely many upper bounds. Then the second part is what makes supremum unique and special. The second part says that supremum must be the smallest upper bound. So all other, infinitely many other upper bounds will be greater than or equal to that supremum. If they're equal, then they are the supremum. Okay, so if you check off both of these boxes, then you're dealing with a supremum, okay? So let's consider an interval 0 to 1, not including 0 and not including 1, because we have these round brackets, not square. And let's talk about a supremum. First, let's understand that it has many upper bounds. 1 is its upper bound, 2 is its upper bound, 3 is, 4 is, 5 is, 6 is, 100 is, 1000 is. You get the idea. It has infinitely many upper bounds. So supremum, according to the first definition, has to be one of the upper bounds. But that doesn't make it special. The second part makes it special and unique. So there's only one supremum. And that part says that out of all the other upper bounds that we listed, this is the smallest. That's why supremum is called the least upper bound. The infimum is the mirror image of that argument. Infimum has to meet also two requirements. That first one, that it is one of the lower bounds, and the second, that it is the greatest of the lower bounds. Okay, so the implication of the first portion of the definition, or the first condition, is that what does it mean to be an upper bound? It means that every single element in a set under consideration or interval under consideration has to be smaller than the upper bounds, right? So every single s in this interval, so small s in this set, has to be smaller than the supremum. But this specific requirement is satisfied by every other upper bound. The second is not, because then we will say that m is the least of all the other upper bounds, okay? Now, the other implication that you will use in your proofs, but not in this video, is here. So follow this thinking here. So when we say that m is a supremum, for us, that is 1, what does that mean? That means that no other value is also a supremum. And what does that mean? That means that if you took the smallest little step to the left of m, so this is a tiny number. I have drawn it in a large way so that you don't squint, but it's a tiny number. So a tiny epsilon step left of m, you get m prime. Okay, so m prime, doesn't matter how small that epsilon is, how small that step is, this is not also a supremum. Which means if this is not a supremum, it means that there is an element here between m prime and m. Element of this interval under consideration. At least one element has to be between the two. Because if it wasn't, then accidentally you have made m prime a supremum. Because if there are no elements of this set in this little interval, that means that every element of the set is less than m prime, making m prime one of the upper bounds. And you can see that m prime is clearly less than m, epsilon less than m, making this a supremum. And that's a contradiction. So how you will write that is that m, there is some element from the set between these two, okay? because if it wasn't, then this would be a supremum, and that would be a contradiction once you've said this is a supremum. Okay, that will become extremely important, so put it down somewhere in your notes and keep in mind that is what you will be using. Now let's just start solving problems. The first problem asks about the interval 0 to 1, where 0 and 1 are both included in this interval. Is it bounded above? Yes, because there is a certain value above which this interval does not grow. It doesn't grow uncontrollably to positive infinity. 1 is that value above which it doesn't grow. Does it have a lower bound? Yes. 0 is that value below which it doesn't decrease. So it's bounded above and bounded below. Since that's the case, then it has infinitely many upper bounds and infinitely many lower bounds. But it has one sup and one inf. Its sup is 1, its inf is 0. It also has maximum and minimum because I have square brackets here. 0 and 1 are included. So it has 1 and 0. So the second example asks about same interval, but 0 and 1 are no longer included. And maximum and minimum require inclusion in the set. So in this case, everything will be the same except from minimum and maximum will not exist. Number 3. Now we're no longer looking at the interval. We're looking at a set with two different numbers. So there are just 2 points, isolated points, 2 and 7. Is a set of finitely many numbers bounded above and below? Yes, because nothing here grows above 7, nothing decreases below 2. It's bounded above and below. Supremum is 7 and infimum is 2. Both are attained. They're part of the set, so min and max exist. Another similar example, if 0 was the element, again, you would just say the same thing. It is bounded above and below, and everything is going to be 0, min, max, sup, and inf. Now, number 5, this is getting interesting. Now we're considering a set. And if you want to take a look at how the set looks like, it's this, right? So the first is when n is 1, you have 1 over 1 or 1. That's the first element. Then it's 1/2, then it's 1/3, and it decreases from 1. 1 is the greatest value it will ever be. So it is bounded above. Above 1, nothing gets greater than 1. It's bounded below as well, because as you can see, 1 over huge number is very close to 0, but it never crosses 0 and gets smaller than 0 and gets -1 or 2, right? So it is bounded below. It has inf 0 and sup 1. Maximum is 1, but minimum does not exist. So let's talk about it for a little bit because that's important. Okay, so infimum does not need to be part of the interval. It does not care about it. None of the 2 conditions of infimum or supremum say that inclusion is required in the set, but minimum and maximum care about that. And this right here approaches 0, but never becomes 0. And that is one of the most fundamental ideas in all of mathematics, probably. And when you first start learning this is in calculus, when you cover limits, and you say that limit, when n goes to infinity, of 1 over n is 0. But if I told you to write down that 1 over n equals to 0, you probably couldn't do it because it gives you terrible feelings, right? So you can say that it goes to 0, but I just can't make myself write that 1 over n equals to 0 because it doesn't. Okay, so since it never becomes 0, then 0 is not part of the set. Therefore, minimum doesn't exist. Okay, 6 is pretty easy. It's a union of 2 disjoint intervals, 0 to 1, 2 to 3. And they're clearly bounded above and below. Min and max exist because there are square brackets everywhere. When you see that, you have min and max, and therefore you have sup and inf. Okay, here in 7, we have a union of interval here. Starts from 2, so it is bounded below by 2. And it is not bounded above. It grows to infinity. If it's not bounded above, it doesn't have any upper bound. It doesn't have sup, doesn't have max, has min, and has inf. Because 2 is included in the set, because it's a square bracket. Okay, now this 8 is interesting, because it's asking you to find intersection of this movable interval. So by definition of intersection, for element to be in the intersection, it has to be in every single set, or in this case, in every single interval. So the task becomes to find what element or what elements are in every single interval. So let's think about that, and once we determine that, the questions will be easy. So I have made a little something to help us. The first term is when n is 1, 1 over 1, or 1. 1 plus 1, that's 2. So the first interval is 1 to 2. 1 and 2 included. Remember that. So the second is when n is 2, 1 over 2, and 3 over 2. Okay, 1 is still included. As you can see, the left edge of this interval gets close to 0, and the right edge gets close to 1. Even if this ever became 0, which it doesn't, as we discussed, it still starts with 1. So 1 will always be included on the right side. And 1 is included as the first term, and we have a square bracket there. So this is included. The left is also included. So 1 is the only element that will be in the intersection, because that's the only element that is in every interval. Okay, so the answer to this is a one-element set whose element is 1. So at this point, you can forget about this and not even look at this, and just look at this set when you're answering all these questions. And that's way easier. And that becomes a similar problem to this, right? So it's bounded above and below, and everything is going to be 1. All right, number 9, x squared. If you put x squared in your Desmos and zoom out and keep zooming out, the legs will keep going up to infinity. So it's not bounded above. It is bounded below by 0. So therefore, max does not exist. Min is 0 and attained. Inf is 0. Number 10. Now we're in rationals. So any number whose square is less than 4 will work. So any number from -2 to 2, not including -2 and 2, because I don't have less than or equal to here. I just have strictly less than. So min and max don't exist. Sup is 2, inf is -2, and we do have this. Now let's consider question 11, cosine of n pi over 3. N pi over 3 is basically, pi over 3 is 60 degrees. N is 1, you have 60 degrees, that's 1 over 2, -1 over 2, then you have -1, so 3 pi over 3, that's pi, -1, and then 6 pi over 3 is +1. So values that cosine gives you here are -1, -1/2, 1/2, and 1. Well, you're thinking about maximums and minimums, so forget about -1/2 and 1/2. Just think about -1 and 1. Is it bounded above and below? Of course, cosine is always bounded above and below. Min and max, it attains its minimum and its maximum, right? And supremum are the same. Now, this is tricky, and I don't think you will ever get this on your exam, but it's interesting to think about it. Is empty set bounded above and below? It is bounded above and below, and I will explain why. But it doesn't have maximum or minimum because it's bounded above by any or every number on the number line, and the same with bounded below. It's bounded below by any number on the number line. So it doesn't have max or min, doesn't have sup or inf. So some books say that supremum doesn't exist, and some books say that it is positive infinity. So either or, And in an infimum, sometimes it says it's negative infinity. Okay, now let's talk about this, and same exact argument applies to the bounded below part. So when we say that this set, which happens to be empty set, is bounded above, we are saying that there is some number m or any number on the number line that is greater than or equal to the members of this set, which is arbitrary representative of the member is S. So the equivalent statement to this is if S is in this empty set, then some number m is greater than that member of the set. Since we have a conditional statement here, if then, and this is an antecedent, this is P. Since this is false, if you remember from the truth tables of conditional statements, when antecedent is false, it doesn't matter if consequent has a truth value of true or false. The entire statement is true. It's vacuously or trivially true, but it's true. So this is why with empty set, which has no element, so no element can be a member of this, is bounded above by any number on the number line, and below is the same argument. Now 13 is a little tricky because again, we are not considering real number line R, we're considering rationals, only rationals. Here, Q, okay? And we are between 0 and square root of 2. Now it is bounded above and below, clearly. It does not uncontrollably grow above a certain point or decreases below a certain point. But tricky part is, does it have a maximum? It does not, because we are in, if I had here R, then yes, maximum would exist, or we would have maximum here. But we have Q there, so maximum does not exist here because square root of 2 is not a rational number, it's irrational. Supremum is square root of 2 and infimum is 0. Now why is this interesting? The implication we discussed above in the beginning of the video was that if I say that some given number is, let's say m, here is a supremum is square root of 2. What I'm saying is that if I take a step, very small step to the left, epsilon tiny step to the left this way, right here, some m prime is not also a supremum. Meaning that right here, there is some rational that is less than square root of 2 and is rational. So yeah, and because rationals are dense, so you can, no matter how small that step is, you can always find a rational number that will be close to square root of 2, but less than square root of 2. Okay? So, and the reason why you are sure that supremum exists is because of completeness axiom. Which says that the number line, real number line, has no gaps. So you have all the faith that that exists. Okay, so this problem right here combines a lot of important ideas. So that's why it's probably my favorite, this one and this one. Okay, so I think that if you took an exam on this topic, you would probably get 100. So there you go. Hopefully you enjoyed this video. Bye.